Tá, parece que está funcionando aí. Ok. Ok, let's go. Every problem you can advise me, okay? So this mini course will be about a book called entitled "The Quantum Enigma" from Wolfgang Schmidt. You can find a Portuguese edition translated by a professor of Pontifícia Universidade Católica, PUC, Rafael de Paula. That's a lot of material about him, about he speaking about the enigma quântico, the quantum enigma, and so on. You can see, if you look for in the internet, you can find a lot of material. Okay. So let's talk about some introductory things about quantum physics. First of all, where is such an enigma? Let's try to explain what is quantum physics, or in what it differs from classical physics. Okay. We start from a famous experiment, the double slit experiment, which is the following. I suppose you can see the cursor of the mouse. All right? Everybody, or no?
Yes, I can see.
Okay, that's great, because it will. Okay. Here there is light coming, and light passes through these two slits, okay, S1 and S2. This phenomena is a very well-known ondulatory phenomena called interference phenomena. Okay, that's what we observe. We observe a succession here of maximums and minimums of light, right? The light passes through the two slits and goes. The light finally goes to how can I say, like agora deu branco. Um anteparo, né? Um anteparo que você pode olhar, que é impressionado pela luz. Like the X-ray film, okay? That's the Young experiment in 1802, about 1802 year. And this experiment shown the wave nature of light, because at that time people was not sure if a light is particle or wave. But with this experiment, it was clear that light is a wave. Light is a wave phenomena, okay? But after, in the beginning of the 20th century, Einstein pointed the particle nature of light as the best explication of the photoelectric effect. So is light particle or wave? So the problem became appeared again. Okay. And even when light behaves like a particle, it can be a wave. Let me explain this. It can be absurd. If we do this experiment one by one photon is the particle associated with light. With light is if light is think to be particles. So the name of this particle we just say it, the photon. We name it as a photon. Okay, it's the quantized light. If we do the double slit experiment using one photon each time, then passes one photon and then passes another photon after, they will behave like a wave. Why? I will explain why. Because this is like a double slit experiment performed with electrons. Okay. Well, let's consider that the double slit experiments we have electrons. Surely a particle is in it. Oops, I have used the same picture as we used to explain the double slit experiments with light. But wait a moment, just let me do just a correction here, and because the result will be the same. Okay, the result with electrons will be the same, but that means that the electrons are a wave phenomena. It's not a particle. It turns out that unfortunately we have this problem. The electron behaves like a wave, also like a light. Okay, because the result we see here is the interference pattern, the same interference pattern that we observed in light. Okay. But in fact, when we don't know which slit the electron passes through, there is an interference pattern. Then the electron behaves like a wave. Okay? We just don't know by which slit the electron is passing through. All right? When we don't know that, the pattern that we observe here is the pattern typical from a wave, which is an interference pattern. Okay. All right. So let's continue this. Wait a moment. Okay. But when we do know which slit the electron passes through, there are no interference at all. So it's a crazy thing, all right? Crazy thing happening here. When we don't know by which slit the electron passes through, the electrons behave like a wave. But by some method, we can see by which slit the electron passes. So it changes their behavior. The electron change change their behavior, and they behave like particle. That's and we thought that it is particle. It is a particle, and the electron it's a particle, isn't it? We don't know. We don't know for sure. So that's the wave-particle duality. Waves can behave like particle, and particles can behave like waves. Okay, it depends on the what I measure. Okay, if someone have some if someone has any question, feel free to interrupt me. Okay. This everybody see this animation? I think so. What if we consider the double slit experiment with one by one electron? With one by one electron, if I let pass just one electron each time, I see first point, because the electron will reach o anteparo, né? Que eu não sei o nome em inglês. We reach at one point. But if we let this repeat, indefinitely repeat, so I will see this pattern here that that you are seeing. We have a lot of points formed, and when we after many electrons has passed, okay, I will see an interference pattern. This is an interference pattern because if this is behavior like a wave, because if electrons were pure particles, they would behave differently. They would not behave like this animation you are seeing right now. They would behave like not four portions, okay, that we are seeing, but we would see two portions, at the maximum two portions. All right. So interference pattern suggests that each electron interferes with itself. Why does the interference disappear when we know which slits the electron passed through? Because when we are capable of measuring which slit the electron passes through, this interference pattern will be destroyed, and we'll see just I will return this, and we will see just two grouping here when we measure which slit the electron passes through. Okay. All right. Is that clear? That's the problem.
Yes, the word looks like screen. Anteparo
Yes.
screen.
Okay. Screen. the screening film or something like this. The screen. A tela. Okay. That's great. Thank you. All right, people. So you have two key things in quantum physics. First, the wave-particle duality. Okay. What is such a thing? It is a wave or particle. neither wave, neither particle. It's a different thing. And we have another key feature typical from quantum physics, which is a state collapse. State collapse. The physical state of a system changes instantaneously after each measure. Right? When I measure something, I change the state. Right? There are several different interpretations for this phenomenon. Several. For example, there is a realistic interpretation by which the state is some definite state, but we just don't know. Okay? And so on. That's the very famous debate about between realistic interpretation and what we say Copenhagen interpretation. In the Copenhagen interpretation, the state, the real state of the quantum system is fundamentally, I mean, the electron somehow passes through two slits simultaneously because there are interference. And somehow it passes through both slits simultaneously. But when we do some measure, then I changes the quantum states, and the electron passes through one slit when I measure the system. But while I am not measuring, the state is a quantum state. That's Copenhagen interpretation. But the realistic interpretation is different. Okay? Okay. Let's call the state vector. Let's symbolize the state vector of each electron by a Greek letter called psi. Psi. Before measure, the state vector of each electron is represented like a sum. The electron is passing through slit A and simultaneously through slit B. Okay? With equal probability. Equal probability. After I measure, suppose I see the electron passing through slit A. So the quantum state is psi A and not psi B. Okay? So after measurement, or it's correct, here is measurement. Okay? The state of each electron is either psi A or psi B, right? Okay. Now, there is a very strange consequence of the vector state collapse also. This is the vector state collapse is we saw that it is related with the duality nature of things, the wave particle duality. Okay, but Einstein, Podolsky, and Rosen, they published a very famous article, very famous work in 1935. What is known as the these initials, Einstein-Podolsky-Rosen paradox. Okay. which is the following. We have two electrons, and I called them entangled electrons. In Portuguese, it is elétrons emaranhados, ou entrelaçados, elétrons entrelaçados. What does it mean? Entangled electrons. It means that it has a constraint between some quantity that can be measured, which in this example is the spin of the electron. The spin of the electron is something similar to when the electron is rotating, is rotating around itself. It produces a quantity analogous to the spin, okay? Spin of the electron. But the spin of the electron is a pure quantum quantity. It has no classical analog, okay? So you can understand this by the rotation of the electron, but this is not, there is not real relation between these two quantities, okay? Just for... Okay, so entangled electrons, the entangled electrons are electrons with some quantity, for example, spin. If one electron has a spin up, the other automatically, we know that other has spin down, because there is a constraint between these two. Okay? So this kind of thing is what we call entangled electrons. Okay? Entangled electrons. So we have two entangled electrons. Don't be worried about, but in practice, it is possible to produce two entangled electrons. Yes, it is. So there is another department. Okay, this the sophistication of the experimentalists. Okay, it is possible. So we have one electron coming to the left and another electron coming to the right with equal velocities. And if the spin, we don't know if the spin of this electron, this first electron, is up or down. We don't know that. But if we measure this, we will do automatically. We will know automatically if the spin of the another electron is downward or up, because the sum of the spin should be zero. That's the constraint. That's the constraint here. The total spin is zero. So if the spin of the one electron is up, the spin of another electron is down. All right? That's what I said. Okay. But now we can ask, is it just the effect of the measuring process, or does it indicate the reality itself? The electrons were there a spin. We just don't know which spin if it is up or down, or the electron. When I measure the spin, the electron changes instantaneously its spin to the spin measured. It is one thing or another. That's a very important question that many the best physicists, but the best scientists will had to deal many years ago. Okay. Now, let's explain some interesting thing. John Stuart Bell found in 1964 some equations which is called Bell's Inequalities, very famous, which could provide the answer to this question. All right. The so-called Bell's inequalities are the statistical pattern that repeated measures would have to obey if both electrons had determinate spins. So, in other words, we can perform a thousand of experiments, repeat thousands of times these experiments, and we can measure the spin of the electron, okay, and another electron will be automatically, the spin of the another electron will be automatically known, right? But when we perform this experiment several times, we can treat statistically, and we can compare padrões estatísticos, okay, statistical pattern of the measurements. And Bell established, parting from the principle that the two electrons have a definite state, but we don't know, we just don't know which state is that, if its spin is up or down. Okay, if these two electrons have a definite spin, so the statistical pattern should have obeyed some inequalities. Okay, and if those inequalities, so that's what I wrote in right. Okay, if it is obeyed by measurement, if these inequalities is obeyed by measurements, so the realistic interpretation is correct. But if the Bell's inequalities is violated by measurements, so the Copenhagen interpretation is correct. Copenhagen interpretation. Okay, that's a so as to say is it's a would be a mathematical demonstration of the interpretation. Okay, just one remark here, one important remark. We are speaking about in the scientific key. Okay, we are speaking scientifically, and science does not provide ultimate proof. Okay, so this demonstration still leaves some room for controversy. Okay, but at least the result of this demonstration will turn some interpretation, just even realistic or the Copenhagen interpretation, much more probable. Okay, much more probable. Okay, let's. And just only in several years after, in 1982, French group, sorry, a French guy, Alan Aspect, succeeded to test Bell's inequalities experimentally in the context of the paradox, this EPR paradox. And the result was, can I say, let's in favor to Copenhagen interpretation. So the last experiments suggests that the electron, when it passes through two slits, it somehow passes two slits simultaneously. Okay, that's very disturbing, very disturbing. And when you measure, you change reality. You change reality. Okay. Somehow the quantum reality avoids showing up. When we try to see it, it changes to a familiar reality, which is a classical reality, right? Okay, people. If someone has some question, please feel free to ask me something, everything, and if you can see that I am having very severe difficulties to speak. So feel free to ask your question in Portuguese if you want, okay?
Professor, o senhor se importa de explicar novamente as desigualdades de Bell? Eu não entendi muito bem, tipo, se ele obedece medida ou se ele é violado por medida.
About Bell's inequalities. The measurement, if the measurements obeys the Bell's inequalities, so because Bell's inequalities are done taken from the realistic perspective. Okay, so if you think that both electrons, each one has some definite spin up or down, but we just don't know which is. But the electron itself, it has objectively spin up or down. So the consequence of this realistic point of the view is the Bell's inequalities. So if measurement obeys the Bell's inequalities, so we have the realistic interpretation is correct. All right? And if the measurement violates the Bell's inequalities, so the Copenhagen interpretation is correct. All right? Eu respondi?
Entendi. Dessa vez foi. Valeu.
Okay, that's great. Now, how bizarre is quantum physics?
Professor, I have a question. About
Go
the
ahead.
experiment from Alan Aspect. I have a doubt if does the result obtained by Alan discard the validity of the theories such as the Brugge-Brown theory or many words interpretation?
No. What the first one you said? Before many word interpretation?
The Brugge-Brown
okay.
interpretation about the pilot
Good
wave.
question. Great question. This the violation of the measurement points in the direction to Copenhagen interpretation. And like the Copenhagen interpretation, very similar to Copenhagen interpretation, there is another interpretations. Like this one. What's your name?
My name is Thiago.
Thiago. Like Thiago asked, there are another interpretations which will be would be corroborated by the experiment of Allen aspect, which is the I'm sorry. Now I don't know. I'm not sure if the realistic, because the non-local Bon de Broglie interpretation, the Bon de Broglie interpretation is a kind of realistic interpretation, right? Is a kind of realistic interpretation with non-locality, with non-local potential here. So I don't know if the Allen aspect experiments would corroborate the Bon de Broglie experiment. I don't know. Maybe yes. But surely would corroborate the many world interpretation, which is kind of Copenhagen interpretation to the craziest degree, okay? Because I consider the many word interpretation crazy, okay? Poor crazy. I don't take it seriously, okay? Several people takes it seriously, but I don't know. I don't take it seriously. I will explain for everybody what is the many word interpretation. Is the following, okay? If we measure, if you can see by which slit the electron has passed through, so will be the state collapse and the state of the electron will change, okay? But automatically there is another universe. There is another universe by which the electron passes through another slit, okay? So that's the type of the theory that cannot be verified, okay? Cannot be never verified experimentally, okay? So I will let us keep in mind just the Copenhagen interpretation. But of course, it is possible to say about another interpretations, okay? Let's
Okay, thanks.
Okay. So how bizarre is quantum physics? A particle can have simultaneously a spin up and down, and it can pass through both slits A and B, and it can be here and there at the same time. But it is a very prankish particle. É uma partícula muito arteira, muito, né? Muito arteira. It pretends to be a well-behaved particle. Ela finge que é bem comportada, mas não é. But these particles are much more evil than we expected. It can change reality not only instantaneously, but in the past. Let me explain this. We are in the very end of this class, and I will not explain in details the further experiments that people have done. Okay, so the people have done further very many experimentos assim absurdamente sofisticados, ok? And the result was even more disturbing, Let's say about few things about that. Okay, let's consider this experiment here. Let me explain something. There's light. It could be electrons anyway. As a matter, it doesn't matter. The light, one by one photon each time. So if a photon passes through the slit 1, okay, so what will happen here? This thing here is I forgot this. This is a crystal which has the following property. It divides. When it received one photon, it divides into two photons with half energy. Two photons. One photon here, two entangled photons. Haha. We have two entangled photons here in red. In red, we have one photon here passing through this way, and another photon here passing through this way, right? And this photon will reach a screen. These two photons, what we have this with after many photons passes through, we have, in principle, if we do not measure anything, we will have here in the screen D0, we will have here an interference pattern, okay? We will have an interference here. All right. But when we measured here, forgot this, okay? Forgot the D1 and D2, forgot this, okay? Forgot. This entire portion of the I cannot say about this because this is another complication. This is a quantum eraser procedure. I don't want to speak about this, okay, right now. So forgot this. This is a complication that for us here it is not important. It is just interesting, just the D3 and D4 here, detectors. We have detector, we have a screen here, which we called D0. D0 is in some sense is a detector, which we call a detector. And we have a detector in D4, and D3 is another detector, right? This thing here is a half deflector. It lets light pass through, and sometimes and half times, and another half times it can it can reflect the photon. Okay, but let us consider if it was a perfect mirror. Perfect mirror would reflect every light, right? Every light. And if we detect the detector, if the detector, this detector here, D3, detect the photon, what does it mean? It means that electron passes through slit 2, right? So that's a way of measuring which slits the electron or the photon is passing through, right? If this detector D4 emits some sound, so I know that the electron passes through slit 1, right? Now, if this is a how can I say? If we take this apparatus here with prisma, né? And these two detectors, D3 and D4. If this apparatus, I get, I take this away, far away from the slits, very far away. Here, put here. I take these detectors and put these detectors here. You see, very far away. So what will happen? These photons will reach the screen D0 earlier first, and after I will measure the D3 and D4. And when we do this, the experimental result is that if we measure by which slit the electron passes through, I measured after the electron reach the screen, and we have the state collapse will follow the same rules, which means that the measured that I perform after the electrons reach the screen will produce the quantum state that I am measuring at the screen, that was measured before. So in some sense, the reality is produced. The past is changed by what is measured. The past is changed by what is measured. If I forgot, I turn off both detectors D3 and D4. If I turned them off, then the pattern I will observe here in the screen will be an interference pattern. It will be an interference pattern. And the interference pattern will show before I turn on the detectors. Okay, so we have the very it happens this very perturbed, very very, how can I say, very bizarre situation, right? Very bizarre situation. What's the explication or what's the interpretation for this strange thing happening? What I see in the screening depends and in what I measure here or don't measure here. And I can delay the measuring process indefinitely. I can delay the measuring process indefinitely. And if the pattern that I will observe this, it will be unaltered. It will be the same. The same. Okay. So that's the bizarre things about quantum physics that I would like to explain today. Just before questions, that's the end of this part, and tomorrow we will try to solve these interpretation problems by calling the ancient philosophy, right? Ancient philosophy, and then tomorrow I will do some introduction to some elements of Aristotelian philosophy, and these elements will be very useful. Will be very helpful in solving the interpretation of these bizarre features of quantum physics. All right. Everyone has some question, some would like to ask some question. Let us see here. Okay. Ok. Ah. No, my English. Ô, gente, eu tô errando o tempo todo. Eu tô falando aqui. O tempo todo eu tô cometendo erro de gramática.
Guilherme, boa noite.
Boa noite.
Eu queria só fazer uma pergunta. Essa teoria de voltar no tempo, com essa rotação dessas partículas, elas teriam que ser de cargas diferentes, tipo um positivo e outro negativo?
Opa. Na verdade, eu vou responder em português, está no finalzinho. Esses experimentos, você pode fazer tanto com elétrons ou quanto com fótons. Então, com fótons, no caso, aí não tem. No caso aqui, seriam fótons emaranhados, um estaria com spin determinado, na verdade, seria polarização, tá? Uma propriedade do fóton, seria a emaranhada, no caso, seria o vínculo aí estaria relacionado à polarização do fóton. Um fóton está polarizado de uma certa maneira, então o outro automaticamente está polarizado de uma outra maneira. Mas no caso do elétron, seria sempre carga negativa, né? O elétron tem carga negativa, mas seria, por exemplo, o spin. Né? Não sei se você perguntou mais ou menos isso, né? Mas se eu não entendi, pode novamente insistir.
Não, é isso mesmo, não é obrigatório, né? Tá joia.
Então eu vou parar a gravação aqui, ó. Stop the recording. Right? Stop presenting. Ok. Ok, então, gente? Alguma pergunta mais? Pode aproveitar agora. Agora está liberado geral. Pode perguntar até coisa de geografia, história, biologia. Eu só não vou saber, né? Eu acho que talvez valha a pena. Vocês querem um detalhamento um pouco maior sobre esses experimentos aí, na aula que vem? Talvez? Não sei. Eu acho que ficou uma transparência só, é pouco. Eu achei que não ia dar tempo para falar nada, por isso que eu coloquei só uma transparência. Então, isso aí é. Hoje a gente já entra. Ainda está gravando? Ih, está gravando. Tá bom. Vou parar agora.